Hello, this is Michael Sinenko again, and we are going to continue off on the second half of this, or should I say the second part to the heat diffusion equation. This is going to be going over how heat flows or heat transfer occurs in spherical coordinates. Now, like I said, this is where the heat diffusion, just write that up here, heat diffusion equation in spherical coordinates. Now, just for the sake of time, I went ahead and I put my control volume here. This is a very small infinitesimal sized cube. This is going to be represented within our cylindrical coordinate system. So normally, like any other coordinate system, you got a Z direction, you got a Y direction, you got an X direction. But we're gonna actually introduce some different types of ways that we can look at this. So with spherical coordinates, we got a radial direction. This is gonna be how far you go out into your sphere. Imagine that there's a sphere here, and imagine this is a tiny little projection. It's within this sphere that may be here, you know. So with that, there's an angle right here, and this is going to be our polar angle. Imagine an object that if there was a Cartesian plane right here, it would be rotating like that. That would be our polar direction. And in here, this is going to be considered our azimuthal direction if you had an object rotating like this. Now, so with this type of situation, heat transfer pretty much occurs in the same kind of way, but it's going to be a little bit more complex because you're going to have these angles involved, of course. So you got some heat that is being introduced into this control volume through one perpendicular plane coming out the other side, the same way that we described in our rectangular coordinates. And this is going to also come in this direction, in that direction. And the direction that is going to be in the theta direction is going to be considered the radius times the differential change in theta, because if there's no radius, there's no heat transfer, because you got to have some kind of distance and then be able to see how far that heat goes out. Same with the azimuthal direction. There has to be some kind of distance in order for you to be able to measure any kind of change in heat that is going to occur in that direction. So what we have here, what you're going to notice is I have this defined as r sine theta d theta. Well, why is that? Well, if we draw out this radial direction to some arbitrary length, you're going to realize that there's going to be another angle right here in the azimuthal direction. And imagine if you had like maybe like say like a light source, and this would be the projection of it. Well, how is that actually defined here? Well, if you have this right here, this triangle, let me just draw it over here, right here. Well, this angle right here is going to be actually complementary with that angle right there. So you're going to have this right here. And what we can do is we could use the sine. When you know that the sine is equal to the opposite over hypotenuse, right? Makes sense. So what do we know here? Well, we don't know what this is at all. Well, we can just call this x prime. And then this is going to be our hypotenuse right here, which is r. So if I were to actually plug these in, got sine theta, got x prime, well, x prime, whatever you want to call it, choose whatever variable, you're just setting it equal to it. You got the radius or radial there. So then x prime is going to be equal to sine theta, or if you want to put r, or r sine theta. However, conventionally speaking, we got it like this, and that's what it is. But we also attach this d phi term because it's going to be how much, or here, I've always got the d phi's and the d theta's confused, and how much that the heat is actually changing in that direction, of course. So, and of course, we got that r d theta, and we just have dr in this direction. So now that we have our control volume defined, we understand how heat is going in, how heat is being introduced. it's going to pretty much follow the same type of system that a rectangular coordinate system would have. Instead of, you know, let's say you would have that qx plus some arbitrary distance dx. Instead of that, you would have q theta plus d theta, or q phi plus d phi, and it would be equal to essentially the same thing. Here you would have q phi. You have q phi plus the differential change in temperature in that direction in respect to a differential amount in that direction. So that's how that is going to play a role, and you will see how this is going to play a role in when we do the same thing that we did with the conservation of energy equation in terms of rates here. Now I'm going to go over here, and for the sake of room, we already knew that the energy stored within our system is equal to the energy going into the system plus the energy generated within our system minus the energy leaving our system. Well, this is going to be pretty much almost the same thing that we had for the rectangular coordinates, but there's going to be a little bit of a change, and that's because we have it in spherical coordinates. We're going to see that as we're going to have this same, the heat generation term within here, which was defined as in watts per meter cubed, times our differential volume. And what we're going to see here is the differential volume is going to end up, which I'm going to show you here soon, it's r squared sine theta d phi d theta dr. That's what we have here. So what about the energy in? Well, the energy in is going to be simple. It's going to be the qr, the q theta, and the q phi that is being introduced into our control volume here. So we're going to leave these two terms alone. By the way, this was not the energy storage term. This was the energy generation term, by the way. I want to let you guys know, got that wrong for a second. But let's go back into the energy storage term. So what the energy storage term is actually going to be the same thing. It's going to be our density, it's going to be our specific heat capacity, and it's going to be all of this right here, which is our differential volume. Sine theta d phi d theta dr. And now that we have these, we can kind of leave them alone. We know what's going in. Now let's get what's going in with what's going out. So this is going to be over here. So we know what is going on. Let's just do this for the QR. And so we would know that something is coming out of the other end. So what do we have here? We got the heat going out plus a differential change in that direction. Well, we already defined what that was. We already defined that it's going to be in this kind of a similar situation. You know, obviously it's just not going to be the phi direction, it's going to be the radial direction. So just to save some room here, I'm going to go ahead and put this in. So you have your QR plus your change in that, the temperature gradient in that direction, dr, and that's what you have. Well, what do we notice here? This one needs to be distributed. So you have QR minus del T, del R, dr. And if you did this for every single term, that is pretty much what you would have. Instead of an R, like I said, you would have the phi, you would have the theta. So that's how that's going to end up working out for us. And this is going to end up going for these two terms. So let's go into defining how Fourier's law would work with this differential control volume since we have spherical coordinates. So I went ahead and I drew this control volume over here so I don't have to keep walking over here and referencing it constantly, because I don't believe in memorization. I believe that you should be able to actually look at your control volume and actually go from there and be able to derive your heat flux, or the way that the heat is actually being transferred through this control volume, coming in, coming out, you know, all those different types of terms, everything that is important in order for us to determine how this heat transfer works in or spherical coordinates, should I say. So we're going to look at Fourier's law of heat flux. We're going to look at how this heat flux works in the different dimensions here. So instead of rectangular coordinates, it's going to look a little bit different. So let's go ahead and start with the radial direction, how that's going to look. So we're going to have this Q double prime right there, radial. That's the type of notation that they use for this type of thing. So what do we notice? So this is going in this way. Imagine it was going in this way. So you have a plane and you want an infinite set of planes this way and how it works this way. So that's how these types of equations work. They work in differential changes. So as with before, like the rectangular coordinates, we have to have our negative of thermal conductivity of our material that this differential control volume is made out of. And then we have to account for that surface in that direction, the differential one. So we have r sine theta d phi, and we have r d theta. So what we can do is combine those r's to be an r squared. So save some time and some room so I don't keep deriving the algebra. So you have sine theta d phi, and then you have d theta partial in respect to that direction dr. And then we're going to do the same thing for the other directions here. We're going to look at our azimuthal direction here. Same thing, have our heat thermal conductivity. And this is going to be what's going in this way, going around. So this surface right here, you have r d theta, and you have dr. So r d theta, you have dr, and how this temperature gradient is changing in respect to the phi direction. So it's going to be r sine theta d phi. And then we're going to do the same thing for our theta direction. So what are we looking at for the theta direction? Well, we're going to look at it going up and down. So we have, of course, this right here, which is going to be the same direction up here. So up there and up, down there. So we're going to have the dr, and we're going to look at also this direction right here, r sine theta d phi, temperature gradient here, and of course, since it's respect to d phi, I'm going to have r d theta here as well. And that is the Fourier's law for heat flux for a differential volume in spherical coordinates. So what do we do from here now? Well, we got this. I derived earlier how the heat is going in and out, but just for the sake of saving time, the r's, the thetas, and the thetas and the phi's and the r's, they're all going to cancel out. And you're going to be basically left with the negative of that gradient in that direction. So Q, let's say R, dr, and it's going to be dr minus, same thing for the other direction. And I'm going to have this and another one for the theta direction. D theta. And of course, this is all going to have our energy generation term, of course. So Q dot, and then R squared sine theta d phi, d theta, and dr. And then all of this would end up equaling to our energy storage term, which is right here. So you have rho, specific heat capacity, r squared, sine theta, d phi, d theta, and dr. And what's going to end up happening here, interestingly enough, is what's going to happen is you can take Fourier's law, these equations, and I'm going to call this 1, I'm going to call this 2, I'm going to call this 3. I'm going to do something similar that I did with the rectangular coordinate system. You're going to take what QR is equal to and plug it in. So 1 will go here, 2 will go here, and 3 will also go right here. And what's going to end up happening is you're going to plug these in, you're going to divide by all of these terms. This is going to factor out the d phi, the d theta, and dr, because if you haven't noticed, when you have this d phi, this d phi, this d theta, and this dr, the other directions automatically get put in when you go into putting the heat flux equation that's associated with the QR, the Q phi, or the Q theta. And it ends up canceling out when you factor all of this out. And what's going to also happen is these negatives are going to also come out, because when you put this in, you got this negative and negative. When I put this negative and negative here, that's going to also come out. So what am I also going to do next? I'm also going to divide or multiply. It's going to be a long equation. Like I'm telling you guys, this is going to be like this long, and I'll do that here in a second. But what's going to end up happening is you're going to divide 1 over, or if not divide, multiply by 1 over r squared sine of theta. And certain terms are going to cancel, some may not, because they depend on those terms. In other words, you may see an r squared in some of these terms here in a bit, and they may not actually cancel out just because, you know, they can't actually be removed because they depend on the direction and the heat gradients in that direction. And you'll see that here in a second. And so I'm going to go ahead and actually get this equation, the simplified version of it. Well, I'm going to cancel out terms over here, so bear with me, it is extremely long. So I'm going to take these terms, I'm going to plug these in, and I'm going to set it equal to this energy storage term. Of course, this energy generation term is also going to be there, but let's go ahead and start over here. So you have a negative. And this is actually where it actually ends right here. So as you guys can see right here, like I was saying earlier, the negative k's cancel everywhere right here. And then what's going to end up happening is we factor these terms out. It's the same in every single case here. If you actually look, you got a dr, you got a d theta, d phi, you got a dr, a d theta, d phi, and same thing here. And since these are all just being subtracted from one another, or should I say added, because those are going to disappear in every case, you're going to take that out, and what's going to end up happening is this is going to divide out, because it's not only going to have all of these terms in common that have this d phi, dr, d theta, but so does our heat generation term. So we can honestly just erase or just remove these right here. All of these are going to be gone. So theta, dr, theta, and that's going to be also removed. So I'm actually going to take some time and I'm going to clean this up a little bit, and we'll go on from right there. And as you can see, things have definitely gotten a lot more simple from here. All we would have to do at this point is divide, or should I say multiply, the whole equation if I were to write a big parentheses right here and all the way over here and multiply the whole entire thing by 1 over the sine of theta. Multiply 1 over the r squared sine of theta. And at this point, now we can basically clean this up and we can get our final equation, and you guys will see the spherical coordinate equation for heat diffusion in all its glory. Woohoo, look at that. So what can we do here? Well, I already wrote this right here, just so it's for reference, so I don't have to keep looking. Like I said, I don't believe in memorization to an extent. So what we can do here, so what do we have? Well, we can just pull these two terms out. So del R. Rk is going to take a ride along. And we cannot do anything with this R. This R cannot cancel with this because it depends on del R, the direction. So that's going to have to stay. But since this is going to be multiplied by this, these two can cancel. So that can come out. You know, so this 1 over R squared can come out. But those are going to cancel out, and we're just going to be left with that gradient. So moving on to the next term. What do we got here? Same thing. We're going to put this del phi here. Heat conductivity is going to come for a ride, but what's different here is this is going to be dependent on del phi, of course. So what do we notice immediately here? Well, this R and that R can cancel, but this sine and that sine are going to multiply. And this R, since it's not going to cancel with anything, it's actually going to come out with it in front. So why don't I actually give myself a little bit of room? I'll say that's going to be 1 over R squared sine squared theta here. And that's going to be our del phi. We'll have K here again. And then, well, everything got canceled. Everything is taken care of. We have just the gradient again here, dt over d phi. And then now we are onto our last term here. Well, same thing. This is going to be in respect to theta. Let's have this here, respect to theta. Hopefully I have enough room here. Maybe put this next bit of terms that may or may not come out front. We're going to find out here in a second. All right. Notice sine of theta, d theta, depends, cannot be canceled with this. And these two R's get canceled. So that R squared is going to come out. So you're going to have 1 over R squared. The sine is going to cancel with this sine. Or, yeah, so the signs are going to cancel. This is in the numerator, this is in the denominator. And then you're going to have del t over del theta. And there we go. Oh wait, no, I'm wrong. They're not going to cancel because this one is dependent on this. So this is actually going to come out. I'm glad I caught myself there. Always be vigilant. Don't go too quick. Catch yourself on mistakes. That's how you'll lose points on tests, but that's how it works. So we got this whole entire first part of the gradient taken care of. So what are we left with? We're just left with that heat generation term. And then we're just left with what's left with the rho, which is our density, specific heat capacity, and then our gradient of temperature in respect to time. And that, ladies and gentlemen, is our spherical coordinates equation, or our heat diffusion equation in spherical coordinates. There you go. Had a little bit of slip ups here and there, but if you catch them, that's what's more important. And there we go.